this case, again, we are talking about a situation where the linear disassembler did not disassemble correctly, but it didn't tell you that there was a failure. Okay? So, and the reason why that happens is because the resynchronization happens fairly quickly, and therefore the number of incorrect bytes that you try to disassemble is rather small. Okay? So now my question is, why does this resynchronization happen quickly? Yeah.
Data, suppose when we put the data which is like fixed size, suppose it takes 4 bytes.
Let's assume that the data is, okay, yeah, go ahead, yeah.
If it is 4 bytes, then subsequent instructions may have may take 3 bytes or 2 bytes, something like that, and taking, that's why it has to take only 3-4 instructions to take compensate for those fixed amount of bytes which are taken by it.
Okay. I think you're telling me the right answer, but I would like to see if someone can phrase the answer in a way that's easier to understand. Any other attempts? Why does resynchronization happen quickly? Okay, so so again, let's, as I told you, valid instructions are typically 1, 2, 3, 4, 5. Let's say this is it, right? So let's say that these are the sizes of valid instructions. Okay, and in some ways this is related to the number 2 and 3. Okay, so let's try to make one observation, right? So if a linear disassembler is currently synchronized, right, then it's going to correctly disassemble everything following this instruction, right, until it reaches some gap, right? So in a sense, once it reaches synchronization, that's kind of a stable state, right? It's going to remain in synchronized mode, right, forever, right? Whereas if you disassemble a byte incorrectly, right, that is, you're out of sync, right, you are not going to remain permanently out of sync, right, because what happens at that point is kind of random, right? So either the instruction that you decode ends at the correct boundary, right, and then you will go back into synchronization, and then you'll be in synchronization forever, right? So essentially, if you start decoding, if you lose synchronization as the example, as in this example, then you start decoding, but then the length of the instruction that you decode is essentially random because it's just some byte that you are incorrectly decoding, right? So therefore, what's going to happen is that each time you decode an incorrect instruction, there is a good chance, right? So maybe say 1 in 5 chance or something like that, that the current incorrectly decoded instruction will end at the right boundary, right? And once you are at the right boundary, then you're going to be in the right boundary all the time, right? So essentially, you can think of it as a state machine, which is in sync, and then it's always going to remain in sync, right? And then it sees data, and then it is in out of sync. Then with some probability, right, P, it will come back to sync because it just depends on where this random thing ends, and with some other probability 1 minus P, it will continue to remain in sync. Out of sync, right? So you can see that if this probability is anything significant, like 1 in 3 or 1 in 4, then you're going to get back in sync after you have 4 instructions. So then the second technique is recursive traversal. Right? So again, remember that the main problem that linear disassembly faces is that if there is data in the middle, it can get confused. Okay, and you might. And let's clarify something, right? So even if you decode one instruction wrong, right, you can't really base any kind of tool on top of that, right? Because if you disassemble wrong, then you're going to instrument incorrectly, and then the resulting program probably will crash. Right? So although linear disassembly may only get 1% or 0.1% or 0.001% of the binary wrong, it probably will still cause the program to crash. So so you don't want any incorrect disassembly, and so the second alternative you look at is recursive traversal. So recursive traversal basically it's going to do something like a graph traversal, right? So what it is going to do is it's going to just like a depth first search, it's going to maintain a visited flag with each location. So so that it doesn't try to disassemble the same location again and again. Okay. And then it's going to decode the current, and if it is a control flow transfer, then it's going to do something different. Okay. So these two cases correspond to control flow transfer instructions. Otherwise, it operates like linear disassembly, right? Because if it's just a straight line code, it's going to just work like linear disassembly. But the moment it reaches a conditional or unconditional jump, then it's going to simply say, okay, maybe I won't continue past this control flow transfer. What I'm going to do instead is to take the target address as the starting point and do a recursive traversal from there. Right? So that's the recursive call over there. Right? So that is, so essentially what it is doing is it's transitioning from this address to the target address, and then it tries to disassemble from there. Okay. So the main problem is if this happens to be an indirect control flow instruction, then the disassembler doesn't know what is the target, right? So with the direct control flow transfer, it works well, right? So you just go and if you think about this type of situation, recursive disassembly is going to work fine because it's going to say, I saw an unconditional jump, so I'm not going to disassemble this, right? It's going to stop disassembly of this block over here, and then it's going to start disassembling the block starting at this address, which is here, and therefore it's going to be fine. Right? So if you have data in the middle of code, then recursive disassembly can handle that. But the problem that it faces is that if there are indirect jumps, then it doesn't know where is that target, right? Because all you know is that, okay, the target is in some register at runtime, but you can't tell what is the value of that register at runtime. So when you're trying to do this before running the program, you don't know where the target is, and therefore you're not able to do this recursive travel at that target. Okay. So what that means is that there may be parts of code that you don't disassemble using this technique. Right? So those are the two techniques, the linear disassembly, which is simple, but if there is data in the middle of code, it's going to get confused. But if there is no data in the middle of code, then it's going to be complete, because it starts at the beginning of the code and disassembles everything all the way to the end of the code. So it's going to be complete, but it may disassemble incorrectly. Recursive traversal can cope with the data in the middle of code, but because of indirect jumps, it may not be able to find all the code, right? There may be some code that it may never be able to reach, and that code may never be disassembled. And if you apply the instrument code, well, that means that code is not going to be instrumented. Okay, so so what I'm going to do now is just to give you some examples of what happens when you take some code and compile it. Okay, so so if you try to look at the binary and find out some of the information that is obvious in the source code, then you have a hard time. Okay, so this is a simple program, right? So there is a main calls HFI, right? So H is here, I is here, and then after that it calls F. Okay, so it doesn't really matter. The actual content of the functions are not that important. Okay. So you have seen these types of function prologues, right? So when you generate code for a function, there is a prologue and there is an epilogue that you have seen when you did your first programming assignments. Okay. So so when we talked about how function calls work, we said that the arguments are pushed on top of stack. Okay, but this is sort of a the compiler doesn't have to actually push it on the stack. It can use any instruction that stores the argument on top of the stack. Okay, so look at what is happening here. So I is the input argument, right? And you're calling F after incrementing the argument by 1, right? So the compiler says, why do I have to push another argument on top of the stack? Because it figures out that, okay, so I'm just going to call F. So so what it does is that it does something called a tail call optimization. So it figures out that call to F is the last thing that happens. Okay, so it figures that there is no need for F to return to H and then to the caller of H, because there's nothing to do after F returns. So the tail call optimization is going to jump to F instead of calling F, because in that case, if you just jump to F, then the return address will be the return address of the return address that's on the stack will be the return address of H, right? So F can directly return to the caller of H without having to come back to H, right? And that saves some instructions. So that is called a tail call optimization, and a tail call optimization will turn what was originally a call into a jump. Okay? So that's something that when you try to look at a binary and figure out, okay, where is this function, you might get confused because you normally expect a function to return and end. Normally you expect a function to end on a return instruction. Instead, you see some jump, and then you don't really know whether it's the end of the function or not. Okay. The other thing that it figures out is that since I'm not calling F, I can do something cleverer, which is my argument I is already on the stack, right? That's going to become the argument to F. So I don't have to push and do all of this. Instead, I can just go directly to that place where the argument is and increment it by 1. That's what I want to do, right? So it knows that at this point, EBP plus 8 is the location of the argument, and it executes this instruction that increments that argument by 1, and then it jumps to F. Okay, so this way, again, if you're looking from the source code, you might expect that there may be a push of an argument and then a call of F, neither of which is present in the optimized code. So, so here is the code generated for main. Okay. Um, so here there is a call of h, and once again you might expect the argument of h to be pushed on the stack, but instead what it figures is that it's going to call I, right, on the x86 architecture. It's typical for the return values to come back in the EAX register. Okay, so I of RC is going to be returned in this EAX register. Okay, and it figures that there is no need to push this. It can just store it on top of the stack, and that'll have the same effect. Okay, you have to work through the stack pointer and base pointer and so on to convince yourself that that goes to the right place. But I guess you can believe me, because well, this code works, and the compiler wouldn't generate such patently wrong code. So once again, instead of a push and whatnot, you see just a move instruction. And once again, so if you're asked to look at this code and then say, okay, how many arguments does h take? Well, it might be difficult for you to figure that out, right? Because for all you know, if you just look at this code, it may seem like, well, there is, h doesn't take any argument because nothing is being pushed on the stack. Okay, and once again, for f, you have a similar situation. The argument is not pushed, and there's a tail call, and so on. So what that tells you is that, in general, it's looking at the binary. A lot of the information that you expect looking at the source code, it may not be there, or it may be done in a way that's different from what you expect. So working with binaries means you really can't make too many assumptions about how what are functions. You may not be able to figure out exactly what functions are because of these tail calls. You can't tell whether it's a jump, right? Typically, a jump is used when you are doing an intra-function control transfer, right? So if you have an if-then else, that usually gets translated into a jump, right? Whereas a call, you don't expect it to be translated into a jump, but that's what happens in the binary, and therefore you may not be able to tell by looking at the binary where the functions begin and where do they end. So there are a lot of even very basic things like identifying function boundaries, finding how many arguments different functions take. All of this, which we of course take for granted on source code, become quite difficult on binaries. Okay? And so working with binaries is definitely tricky. Okay? So so this is, whatever I told you so far is just for the purpose of understanding code, right? So to find out where does the function start and where does the function end, that's for just making sense of the code. Okay. Now, if you want to add some additional code, okay, then it becomes even more tricky, because what if you want to, in SFI and CFI, we wanted to add some additional checking instructions in the middle of the code. So what happens? One of the problems is that if you insert code in the middle, that means, let's say you have a function f. Let's say you have a function f, and following that is a function g, and let's say this is function f, and this is function g. Now, if you insert some code here, right, that means the location where g starts is going to change, right? So this has to be pushed down. Now, the problem is that somewhere else there may be G could be actually originally at this address. Right? So so that's an indirect jump. Right? So in the original code, this is an indirect jump to this location. Right? But now if you add insert some code here, this has changed from, let's say, this address to right? Let's say it just changed by 5 bytes. You cannot arbitrarily, say go ahead and change this correspondingly, because in the binary code it is just a number.